Hi there. We looked today in class at concavity and looked at how to determine on what intervals a given function is concave up or concave down. We also looked at how to find a given function's point or points of inflection. And a point of inflection, remember, is where a function changes from concave up to concave down or vice versa, concave down to concave up. Okay, and so I've selected two problems to demonstrate these procedures, or this procedure I should say, to find intervals of concavity. Number 11 is the first one, f of x equals x cubed minus 6x squared plus 12x. So when we're looking or dealing with concavity, we want to be working with our second derivative. That's the level at which concavity occurs. First derivative is increasing, decreasing, relative maxes, relative mins. Second derivative is concavity and points of inflection. Okay, so to start us off here, I do need to take the second derivative and set it equal to 0. And so we've got here, our first derivative would be 3x squared minus 12x plus 12. And then our second derivative would be 6x minus 12, and then derivative of the constant would be 0. Okay? And then once we're at this level, we're going to set our second derivative equal to 0. This is going to allow us to find numbers for our number line test. In addition, on our number line, we'd be putting discontinuities, although there's no denominator with this function, so I don't have to worry about discontinuities in this particular case. But a discontinuity would be potentially where our graph would change concavity, and so we would want to test that just in case. Yeah. Okay, so in this case, no discontinuity, so we'll go ahead and solve for our 0. So we'll add 12 to both sides and divide by 6, and we get 1, 0 at 2. And so that 2 is going to go onto my number line. And then I'm going to be picking numbers on either side of 2 to test those two intervals. And I'm going to be plugging those testing numbers into my second derivative, f double prime. Okay, so left of 2, I can pick any number. I'm going to go ahead and pick 0, and I'm going to be plugging my 0 into my second derivative up here, this 6x minus 12. And when I plug in 0 there, I get a negative number, which means my graph left of 2 is concave down. Picking a number right of 2, like 3, I'm going to plug in 3 here, I get 6 times 3 minus 12, which is a positive number, showing that my graph right of 2 is concave up. Okay, and so this is going to allow me to set my intervals. We've got concave down from negative infinity to 2, concave up from 2 to infinity. And then I do have a potential point of inflection here. Right, my graph did change concavity at 2. It went from concave down to concave up, and so x equals 2 is a possible location of a point of inflection. We do want to make sure, though, that it is actually a point. If this had been a discontinuity, it wouldn't be a point of inflection. Point of inflection literally is called a point of inflection. If there's a discontinuity, there's not a point there. Right? So we are going to make sure, is there actually a y value? Is this actually a point? And I already knew going into this that there weren't any discontinuities, so I am good to go. If I take that 2 to get my y value and plug that 2 into my f of x, I'd get 2 cubed, which is 8, minus 6 times 4, that's negative 24, 2 squared is 4, plus 12 times 2, which is positive 24. The negative 24 and the positive 24 will cancel each other out. And so I'll have 8 as my y coordinate there, of my point of inflection. Okay, so then I've picked one more for this. Number 19, we have f of x equals x over x squared plus 1. In this particular case with this function, we do have a possibility for a discontinuity. I would want to look at my denominator here and make sure that if there is a discontinuity, it was discussed on my number line. In this case, though, I actually don't have a discontinuity because x squared would have to be negative 1 to make my denominator 0. And you can't have a squared number that equals a negative. Right? So we don't have any discontinuities with this particular function, but anytime you do see a denominator, make sure you've checked for that. Okay? So at this point, we're going to go ahead and take our first and second derivative. So first derivative, we have low d high minus high d low all over low squared. And cleaning this up just a little bit, we have, this is going to be x squared plus 1 minus 2x squared. 1 minus x squared. And so with that, we can go ahead and take our second derivative. And with our second derivative here, we're going to still be doing quotient rule, but take note, in my denominator, I have chain rule down there. Right? And so we've got our low d high minus our high d low all over low squared. Okay, so looking at this function, there's a couple of things I noticed. The first one is I have an x squared plus 1 in both terms of my numerator, right? This is all one term here from the parenthesis over to the x behind the negative 2x. That's all one term. It has an x squared plus 1. I have a second term over here from the parenthesis to the x behind the 2x. That's all one term. And it has an x squared plus 1 as well. And lo and behold, there's also an x squared plus 1 in the denominator. In fact, there are 4 x squared plus 1s. And so whenever you notice that, there's a common term, but remember, that common term has to be in every single location, right? Both of the numerator terms and the denominator term. And if the denominator had multiple terms, it would have to come out of all those as well, right? But if you notice that they are located in all those spots, you can go ahead and simplify that. I'll go ahead and cross off one of those x squared plus 1s. There's only 1 over here to cross off, and 1 in the bottom there. Okay. And so just to kind of clean up my work a little bit, I'm just going to take a moment and rewrite what I've got now. I have that negative 2x times the x squared plus 1. That's what's left over in this first term. And then over here I have minus, and actually this is going to be minus 4x, because there's a 2 times a 2x, which is 4x. And then 1 minus x squared. All over x squared plus 1 quantity cubed. Okay. At this point, you can choose whether or not you want to factor the 2x here. Go ahead and factor it out now. Or if you're more comfortable with distributing first and then factoring, feel free to take that step. It really is your choice. I'm going to go ahead and pull out the 2x now, and I'm actually going to pull out a negative 2x. And so inside those parentheses, in the first term, I'm going to be left with x squared plus 1. And in the second term, when I've pulled out the negative 2x, I'm going to be left with a 2, and then the 1 minus x squared. So this is going to be 2 minus 2x squared. When I've distributed that 2, the leftover 2, into the parentheses. And so then, cleaning this up one step further, we do have, let me slide this up, we do have negative 2x times 3 minus x squared, all over x squared plus 1 quantity cubed. And it's at that point that we can start to look for our zeros to put on our number line, and then also if there had been discontinuities, those would be on my number line as well. Those would be possible breaks of continuity, or sorry, yeah, of concavity. Possible breaks of concavity. Okay? So taking a look here, we're going to go ahead and find our zeros. And remember, for a fraction, the only thing that has to equal 0 is the numerator, and then the whole fraction would be 0, as long as you've simplified. If there's a 0 in the denominator as well, it wouldn't be a 0. Right? But we've simplified all the way here. Okay, and so we're going to go ahead and set this up. I have a couple of zeros. The first one comes from the negative 2x. Negative 2x will equal 0 at x equals 0. And the 3 minus x squared will equal 0 when the 3 is equal to the x squared. Right, I'm going to add this x squared over to the other side, which would be at plus or minus root 3. Right, so all 3 of those numbers are going to be going onto my number line. Okay. So let's go ahead and set this up. We have our 0, our negative root 3, and our root 3. And so I'm going to be testing 4 numbers here in my second derivative, my f double prime. And you can plug into any any version of your second derivative. Make sure though that you do plug into the whole second derivative. I'm not going to be plugging my testing numbers just into the negative 2x root 3 minus x squared. I'm going to be plugging it into the whole thing, numerator and denominator. Okay. So left of negative 3 would be like negative 2. And when I plug in negative 2, I get a positive times a negative, so a negative on top, divided by a positive on bottom. And a negative divided by a positive is a negative. And so I know left of negative root 3, I am concave down. Okay. In between negative root 3 and 0 is like negative 1. When I plug in negative 1, I get a positive times a positive over a positive. Positive times a positive divided by a positive is a positive, and so I know I'm concave up. Okay. Then we have 1 in between 0 and root 3. When I plug in 1, I get a negative times a positive divided by a positive, which is a negative. And right of root 3, I've got, say, 2. When I plug in 2, I get negative times a negative, which is a positive, divided by a positive. And a positive divided by a positive is a positive, so we are concave up. Okay. And so that then is going to give me my intervals. We are concave up on negative root 3 to 0 and root 3 to infinity. We are concave down on negative infinity to negative root 3 and 0 to root 3. And then we have 3 possible points of inflection that I'm going to be checking. Right? 1 at negative root 3, because I changed from concave down to concave up. 1 at 0, because I changed from concave up to concave down. And 1 at root 3, because I changed from concave down to concave up. And so I'm going to be plugging each of those x's, negative root 3, 0, and root 3, into my f of x to make sure that it is actually a point, that point does actually exist. And technically speaking, I already know it's going to exist because I didn't have any discontinuities, but it's good just to double check. And so we're going to go ahead and take that negative root 3 and we're going to plug it in here to my f of x. We're going to have negative root 3 over 3 plus 1. So we're at negative root 3 over 4. Then I'm going to plug in the 0 here, and I'm going to have 0 over 0 plus 1. And 0 divided by 0 plus 1 is 0. Then I'm going to have my root 3, which will be root 3 over 3 plus 1, which will be root 3 over 4. And there's my answer.